Hello, this is Dr. Joe Trout from the physics program at Stockton University. And today we want to talk a little bit about temperature and kinetic theory and about heat. So heat we'll look at as energy transfer due to a temperature difference. And we'll discuss thermal contact, and that is that two objects are in thermal contact if heat energy can be transferred between them. And thermal equilibrium is the conditions where we put two things in contact and no heat passes between them. So this brings around about the zeroth law of thermodynamics, which says that if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A is in thermal equilibrium with object C. This means that we can make devices like thermometers, and we can use it to measure the temperature. So first, let's talk about a little bit about atomic theory. So as you know, we have this planetary model of the atom, and it shows the protons and neutrons in the center and electrons orbiting around the nucleus. Protons and neutrons are about the same energy, at least it's good enough for this class. And if they're about 1.67 times 10 to the minus 27 kilograms. The charge of the proton is plus 1.6 times 10 to the minus 19 coulombs. And we'll discuss what a coulomb is in physics 2. Electrons have a much smaller mass, and it has a charge equal to the magnitude of the proton, but it's negative. So the mass is 9.11 times 10 to the minus 31 kilograms. We'll also use a unit called the atomic mass unit, and it's based on the carbon-12 atom, which has a mass of 12 atomic mass units. So one atomic mass unit is 1.66 times 10 to the minus 27 kilograms. We already talked about temperature scale. We said that Celsius and Fahrenheit are both based on the freezing and boiling point of water. So we take a device and we take a liquid that expands when it's heated, and we make a thermometer and we put it in 0 degrees. We mark that. We put it in ice water and mark that as 0 degrees, and put it in boiling water, mark that as 100 degrees, and then put 100 divisions between them. The Fahrenheit scale is more precise in that it has more divisions. So we start at 32 degrees Fahrenheit and go up to 212 degrees Fahrenheit. And 212 minus 32 is 180 divisions. If we plot temperature in Fahrenheit versus temperature at Celsius, and we assume a linear scale, then we can find a conversion between Fahrenheit and Celsius. So this is a straight line, so it follows y equals mx plus b. So we find the slope. The slope comes out to be 9/5. And the y-intercept is 32. So if we're looking for the temperature in Fahrenheit and we know the temperature in Celsius, it's just 9/5 the temperature in Celsius plus 32. Or we could solve that for the temperature in Celsius. Temperature in Celsius is 5/9 times temperature of Fahrenheit, and Fahrenheit minus 32. So first subtract 32 and then multiply by 5/9. There's also the absolute or Kelvin scale. And in this case, we use a constant volume gas thermometer to figure out what that is. And in this case, we have a vessel and we heat it or cool it and measure the pressure inside. So as it heats, the pressure will increase and we can measure that. What we found is that if we use air, for instance, what will happen is eventually the air will turn into a liquid when it gets cold enough. And if we use different gases, we find that there's different slopes, but they all will eventually turn into a liquid when they're cold enough. And we'll try like oxygen and nitrogen. And once again, what we're saying is that if we start here and we heat it, the pressure increases. And if we start here and we cool it, the pressure decreases. If we extrapolate all these lines back, what happens is they cross the x-axis at negative 273.15 degrees C. And we'll call that 0 degrees, um, sorry, 0 Kelvin. So liquid nitrogen becomes a liquid at about negative 195 degrees. And once again, if we extrapolate all these back, they all cross the x-axis at negative 273.15 degrees, which we'll call 0 Kelvin. Therefore, if we want to know the Kelvin scale temperature and we know what the temperature in Celsius, it's this temperature in Celsius plus 273.15. So here's the three equations for conversions between Celsius, Fahrenheit, and Kelvin. So for example, if the temperature in Fahrenheit is 32, we get 32 minus 32, and we get 0. And that temperature in Kelvin is 273.15 K. Things expand usually when you heat them. So normally when you heat them, things expand. And for instance, that's why there's cracks in sidewalks. It's so that when they heat up and expand, they won't force into each other and crack. So we can get a linear approximation for this. So what happens is we'll start out with some initial length and some initial temperature, and we'll heat it by some delta T, and it'll stretch, right? It'll expand. And when it expands, we'll consider that extra length delta L. So now the original length we'll call L naught, and the change in length we'll call delta L. So in this case, we assume that the change in L is equal to or proportional to the change in temperature and the initial length, and some constant that depends on the material. So we can solve for the new length. It's equal to the old length times, open parentheses, 1 plus alpha delta T, where we look at alpha up in the table for the different values, for the different materials. If we have things expand in 2 dimensions, right, then we have A equals approximately the original area plus gamma, the original area times delta T. And we look up gamma in a table, and it depends on what the material is. We also find that gamma is about 2 alpha. And finally, if we have a volume, it expands, and the equation looks relatively similar. So we have the original volume plus beta, which we look up in a table. It depends on the material, times the initial volume times delta T. So we find that gamma is about 2 alpha and beta is about 3 alpha. So here's some values just for alpha and beta. And what you can see is that beta is about 3 times alpha. 19 times 3 is about 57. That's 56. 17 times 3 is about 51. So beta is approximately 3 alpha. This is a simplified table. So for instance, depending on your mix of concrete, the linear expansion is going to change. But we'll say it's about 12 times 10 to the minus 6. Notice that we don't have a linear coefficient of expansion for gasoline or mercury or a liquid or a fluid because it doesn't make any sense to have it. It's going to be a volume expansion. Here's some things that it's used for. So for example, if we look at alpha of brass, it's 19, and alpha of copper is 17. That means that brass is going to expand more for the same given temperature change. So we make things like a thermostat using bimetallic switches. And what will happen is we have a heater here, and we have this switch that's closed and it turns on the heater. When the temperature gets hot enough, what will happen is the brass will expand more than the copper and it'll bend away, right? So as the brass expands more than the copper, it bends away and it turns your heat off. By the way, here's the bimetallic strip. And because the difference is really small, what they do is make it really, really long, and then they roll it up in a ball, right? So it'll fit on your wall. So for example, how much of a change in length are you going to have for a piece of concrete? And so how far apart should you put the pieces of concrete? So here we see about 0.4 meters is a good approximation for a sidewalk slab. And the delta L will equal the initial length times alpha times delta T. Okay. I know it's also going to expand in the other direction, but I don't care because it's not, I'm just trying to make sure it doesn't collide with the other piece and tilt up and break. So let's say in winter, we go from about 0 degrees to about 38 degrees in the summer, right? So we start with 0.4, we look up the alpha for concrete and multiply it by the change in temperature, and we come up with about 1.8 millimeters. So it doesn't have to be much of a crack between the sidewalk, but there has to be enough so it doesn't buckle. Now let's talk about density. Density is equal to mass over volume. So in general, as the temperature of an object increases, the volume increases, so the density decreases. And in general, as the temperature of the object decreases, the volume will decrease and the density will increase. If you remember our talk about buoyancy, if the density of the object is greater than the density of the fluid, it'll sink. And if the density of the object is less than the density of the fluid, it'll try to float. So let's look at water. Here we have a chunk of water, and it's at about 6 degrees. And winter's coming, just like today. So it cools off a degree, so it gets smaller. So now this air at the top, this water at the top, its volume has decreased, so its density has increased and it sinks to the bottom. And then water comes up to fill in. So we actually see this during the fall and the spring where we have lakes that are turning. The stuff from the bottom goes to the top and the stuff at the top goes to the bottom. So let's keep this going. Now the ice goes from 6 to -1. However, during that time, it turns into ice, right? If this was to keep up, what would happen is the density, it would keep continuing to decrease, and suddenly the density of ice would be more than the density of the water. It would sink to the bottom. But that doesn't make any sense. We know the ice floats on the top of the lake. So here's what happens. If we look at water, as we decrease the temperature, the density definitely increases and it sinks to the bottom. But when we get to 4 degrees Celsius, then the opposite starts to happen. And this is something special with water. So in this case, the opposite starts to happen and the density starts to decrease. So if we are warm, we have a low density. And as we cool off, our density increases because the volume of the water is decreasing. And then at 4 degrees, the opposite starts to happen, and we start to freeze. We'll start to freeze at zero, but we start to expand and the density decreases. So that means that when it cools from 4.5 to 3.5, the volume increases and the density decreases and it floats. And then as it freezes, it'll stay at the top of the lake. This is great for like fish and things because they can swim around down here without the lake being frozen and they don't get frozen into a block of ice. So we've been talking about the ideal gas law. So what we find is if we heat a gas at a constant pressure, the volume increases as the temperature increases. And if we lock it in place and add heat, what's going to happen is the pressure is going to increase as the temperature increases. And if we look at a piston and we have a high pressure compressed gas and then we let it expand, what's going to happen is the pressure will decrease as the volume will increase. So what we see is that it looks like PV is proportional to T. So now we have PV equals nRT is the ideal gas law, N is the number of moles, R is the gas constant, 8.314 joules mole K, P is the pressure in pascals, V is the volume in meters cubed, and T is the temperature in Kelvin. By the way, chemists and food scientists and other people and atmospheric physicists like to use different values for R. Okay? So in this class, we'll use 8.314 joules mole over K. I think chemists like to use 0.0821 liters atmospheres mole K, and food scientists like to use 1.99 calories over mole K. N is the number of moles, and it's the number of molecules divided by Avogadro's number. And Avogadro's number is 6.02 times 10 to the 23rd atoms or molecules. So just like if you have 36 eggs, you divide it by 12, you get 3 dozen. Here, if you had a number of molecules and divide it by Avogadro's number, you get the number of moles. So here's the periodic table, which shows all of the elements. So if we want to find the mass of nitrogen, for example, we'll take the molar mass of nitrogen, which is 14 times 10 to the minus 3 kilograms, and divide it by Avogadro's number, and we get the mass of a nitrogen molecule. So these masses that you see are listed as molar masses. By the way, if we have diatomic nitrogen like exists in the atmosphere, then we multiply the molar mass by 2. We get 28 times 10 to the minus 3 kilograms divided by Avogadro's number, and we end up with the number of the mass of the molecule. We also need something called Boltzmann constant, and Boltzmann constant is just R divided by Avogadro's number. And it's equal to 1.38 times 10 to the minus 23 joules per K over K. If we go ahead and write N, the number of moles, as the number of molecules divided by Avogadro's number, then R over Avogadro's number equals K, and we get NKT. So PV equals N, the number of molecules, K, Boltzmann constant, times T in Kelvin. The ideal gas equation is known as the state equation. It defines the state of a gas. It can't tell you what's going to happen to the gas as time progresses. There's no time in this equation. So, for example, let's say we have a sealed piston and it's under high pressure. So it's 3 atmospheres of pressure in there. And we're going to let it expand at a constant temperature. So what'll happen is the gas will expand at a constant temperature. And in this case, we had to add a heat to do it. And we can figure out what that final volume is. So we'll take the second state, P2, V2, N2, RT2, and divide it by the first state, P1, V1, and RT1. However, we have a sealed piston, so the number of moles of gas doesn't change. R is a constant, and the temperature is constant. So we can solve for V2, we end up with 6 liters. If we lock the piston in place, then our volume doesn't change. And if we add heat to raise the temperature, we can solve for the second temperature. Okay, so let's say we have a person and their lungs holds about 6 liters of water, and 1 liter is about 10 to the minus 3 meters cubed. And we heat it, and it heats in the body to 98.6. And atmospheric pressure is 101 kilopascals. And given that air is 21% oxygen, find the number of oxygen molecules in the lung. So the first thing we have to do is convert the temperature to Celsius and then to Kelvin. So we get 5/9, 98.6 minus 32 is 37. And add 273.15 to it. And we get about 310.15 Kelvin. We know that the number of molecules is PV over KT. So we plug in, and don't forget, the pressure has to be in pascals, and it was given up here in kilopascals. So don't forget to multiply by 1,000. And the volume has to be in meters cubed. So convert that to meters cubed. Boltzmann's constant is 1.38 times 10 to the minus 23, and the pressure. So we end up with about 1.42 times 10 raised to the 23. Sorry about that. Raised to the 23 molecules. However, if we look at it, oxygen is 21% of the air. So we can multiply that by 27 by 0.21. I'm sorry. Oxygen is 21% of the air. So we can multiply that value by 0.21, and we end up with about 3 times 10 to the 22 molecules. Then we can multiply that by the mass of oxygen molecules. So we get 32 grams per mole from the periodic table, and divide it by the Avogadro's number, and we get the grams per molecule. So now we have the number of oxygen molecules times the mass of one oxygen molecule. We get about 1.58 grams. Okay, so really we should put this on a plot that is 3-dimensional. So we have pressure and volume and temperature. And if we cut these up, so for instance, if we hold volume constant, we'll take a slice this way, and we end up with this pink graph here. So as temperature increases, pressure increases. And if we hold temperature constant, we'll take a slice this way, and what we get is our lines of constant pressure. I'm sorry, lines of constant temperature where the pressure changes with the volume. And finally, volume versus temperature, holding pressure constant, is linear also. is linear also. So what is temperature, right? We've defined it, we talk about it, we know we kind of understand that if the temperature's higher, it's hotter out, right? But what is temperature? So let's consider a cube of gas. And there's molecules flying around randomly, right? And I know they're random. You know why? Because when we sit in the classroom, all of a sudden, all the oxygen molecules don't rush to one side of the room and leave everybody to suffocate on the other side, right? Things are pretty well mixed. So these molecules are all running around randomly. But let's just consider one. We have one molecule and it hits the face of the wall of one of the cube. So the y direction is not going to feel a force. However, the x direction is going to feel a force. So when it hits the wall, the only thing the wall can do is push back straight, right? So it's not going to change your y velocity component, but it will change your x velocity component, and you'll move back at the same speed. So we're going to consider the collision with the wall to be elastic. This means that the change in momentum is equal to the change in mass times velocity, but what we get is the mass times the velocity in the x direction minus negative mass times velocity, which is just equal to 2, the mass times the velocity in the x direction. So this is an elastic collision like we talked about a couple of chapters ago. And here's a good application of a collision, an elastic collision. So if this is a length L, right? So if this is a length L, we're going to find the time that it starts from one end, hits the wall, and then gets back to the other end. Okay? So this will be twice the length divided by the velocity in the x direction. So delta t is equal to delta x over vx, which is 2L over vx. Which means we have 2L divided by the velocity for the time and 2m times vx. So this comes out to be equal to the 2's cancel, and vx divided by 1 over vx becomes vx squared, and we get L. So the force due to this one molecule is the mass times the velocity squared over L. However, we should look at the force on all the walls. So in this case, we end up with the force is going to be the square root of the force in the x direction plus the force in the y direction squared plus the force in the z direction squared. So our force now becomes the mass over length, vx squared plus vy squared plus vz squared. However, if I wanted the average velocity, right, we're going to take the root mean square. So this is what's going to happen. The velocity we said was random. And if we took the average of all the velocities, we should end up with 0. So let's go ahead and square it. So we get a whole bunch of particles in here, and we'll get Vx1 plus Vx2 plus Vx3 plus Vx up to n molecules divided by n. That'll give us the average. Therefore, if our x average is going to be equal to the mass times the length, n times Vx average, the average of Vx Vx squared. However, we assume that our velocities, the average velocities in all three of these directions, are equal. If they weren't, then there's the possibility that all the oxygen molecules would rush to one side of the room or rush up to the ceiling or down to the ground, right? But we know it's well mixed. So we end up with this average x velocity squared is just 1/3 the average velocity. So we're almost finished. We have the force is equal to the mass over the length. This is the mass of the molecule times n times 1/3 the velocity. Let's go ahead and multiply, or let's go ahead and find the pressure. The pressure is equal to the force over the area, and the area will just be L squared. So now we'll plug in for the average force. We get M over L N, 1/3 over V, the velocity squared average, or the average of the velocity squared, divided by the length squared. But that gives us the length to the third, which is just the volume. So now we end up with the pressure is 1/3 the mass over the volume, the number of molecules times V squared, the average of the velocity squared. However, we know that PV equals NKT, so P over V equals KT. So we get KT is equal to 1/3 the mass times the average of the velocity squared. And now we'll divide both sides by 2, and we end up with 3/2 KT. So this is the temperature, this is a constant of proportionality, and 3/2 is equal to 1/2 mv squared. However, 1/2 mv squared is just the average kinetic energy. So what we find is that the temperature is a measure of the average kinetic energy of the molecules. And VRMS is the square root of the average velocity squared, which is equal to the square root of 3 kT over m. So the point of that whole derivation is to show you that the temperature is a measure of the average kinetic energy of the molecules. So 3/2 kT is equal to the average kinetic energy of the molecules. So normally we look at a couple of things. We look at the most probable speed, the mean speed, and the root mean square speed, right? And the equations are right here. So if we have a bunch of gas and we look at the probability density, how many molecules and how fast they're going, right? Since the root mean square, since all of these are divided by the mass of the molecule, the larger the molecule, then the lower the average speed is going to be. So for example, for helium, right, that has a very high speed. However, this graph, this probability function, is spread out. So what we'll have is a few molecules going really fast and some going really slow, and the average is pretty high. But all of these graphs all have the same shape. Also, it depends on the temperature. So for a given gas, the higher the temperature, the higher the velocity would be. And the more this gas spreads out. Okay, so normally we have things that can exist in three states: a solid, a liquid, or a gas. And probably the easiest one to think about is water. We have water ice, we have steam, and we have water. And we find that we know that water freezes at 0 degrees. However, that actually depends on the pressure. So we get graphs that look like this, and we have this isotherm where T is a constant temperature. Okay. And what we see is it usually looks like this. So if we're in the um, liquid region or the solid region, right here we go, the liquid region. Here's a liquid vapor region and a vapor region. And depending on how we do it, we're going to see that we'll have these different shapes of graphs. So if we look at one atmosphere, we see that there's a transformation from water to water vapor at 100 degrees. So water will begin to boil at 100 degrees. And at atmospheric pressure, it freezes at 0. However, if the pressure was lower, okay, then, so let's say it's like half an atmosphere, then the freezing point will be higher and the boiling point will be lower. So if you ever camped up in the mountains, what you know is that as you go higher up into the mountains, the pressure decreases and water boils at a lower temperature. So if the water is going to boil at a lower temperature, if you're trying to cook potatoes, for instance, it's going to take longer to cook those potatoes because the water boils at a lower temperature. However, if we go up to a higher pressure, so if we go down into a mine and we boil water there, it's going to boil at a temperature higher than 100 degrees. So these temperatures for freezing and boiling depend on the pressure. There's also this triple point where water exists as water, ice, and steam all at the same temperature. And this triple point is 273.16 K, and it happens at a pressure of about 6.03 times 10 to the minus 3 atmospheres. So here's some critical temperatures and pressures for water and CO2 and oxygen and nitrogen and hydrogen and helium. Okay, so let's talk more about heat. We defined a calorie with a small lowercase c to be the amount of heat needed to raise the temperature of 1 gram of water 1 degree C from 14.5 degrees to 15.5 degrees. A food calorie is actually a kilocalorie, and we found that the calorie was just too small of a unit to use for food. So it's the amount of heat needed to raise the temperature 1 kilogram 1 degree C. We also had the British thermal unit, the amount of heat needed to raise the temperature of 1 pound of water 1 degree Fahrenheit. And 1 BTU equals about 0.25 kilocalories or 252 calories or 1,055 joules. We talked about this in class that we found this mechanical equivalent of heat by a guy named Joule, and what he did was take a mass, he gave it some potential energy and then let it lose potential energy, gaining kinetic energy, and then the paddle wheel gained kinetic energy, and as he did this, the temperature of the water went up, and he realized that there's a relationship between mechanical energy and heat energy. Specific heat is the amount of heat required to raise the substance 1 degree C, 1 kilogram, 1 degree C. And we usually use the joules kilogram degree C in this class. So for example, aluminum takes 900 joules to raise 1 kilogram, 1 degree C, and copper about 390 joules, right? So, and compared to say, to other materials, which take much more heat to rise. So what we find is that it doesn't take much heat to raise the temperature of aluminum or copper. And that's why we make our pans out of aluminum or copper, right? In fact, a lot of times they'll have aluminum because it's cheaper, and then they'll coat it with copper because it has a lower specific heat. So we also have specific heat for gases, and we've talked about this, right? We have specific heat at a constant pressure and specific heat at a constant volume, right? And these are for some different gases. So steam, oxygen, helium, and carbon and nitrogen. We said on the average, a monatomic gas, CP is about 21 joules mol K, and CV is about 12. And we said that was about 5/2 times R and 3/2 times R. And for diatomic molecules, right, we get about 21 for CV, right? And for polyatomic molecules, so anything greater than diatomic, you better look up in a table. So for specific heat, if we want to know how much heat is required to raise 10 kilograms of aluminum from 20 degrees C to 30 degrees C, what we see is that we just need to multiply the mass times the specific heat times the change in temperature. So in this case, it's 900 times 10 times 10. And we end up with 9 times 10 to the fourth joules, or 90,000 joules. How do they figure these specific heats out? What they do is take an aluminum container and they fill it full of water and they put a thermometer in it. And they take a hot sample. So they heat the sample and they know what the mass is. Then they drop it in the container and they wait for it to reach equilibrium temperature. So we have cold water, we have a hot sample, we drop the sample in, we get an equilibrium temperature eventually. So in this case, the heat that's lost by the sample is the heat that's gained by the water and the container. And so what we get is the heat that is gained is by the water and by the aluminum. Okay. And we have the mass of the water and the mass of the aluminum, and the change of temperature of these two are the same. So initially, they're both at the same temperature, the water and the aluminum. And finally, when they reach equilibrium, they'll also both be at the same temperature. And where does this heat come from? It comes from the sample. So we get the mass of the sample, the specific heat of the samples, times the change in temperature of the sample, right? And for our water, the final temperature is equilibrium temperature, and the initial temperature is the cold temperature. And for the sample, the final temperature is equilibrium, and the initial temperature was the hot temperature. So then we do some cancellations, and we can find the specific heat of the sample. So we use conservation of energy to figure out these specific heats, and then somebody writes them up in a nice table for you to use. Now, things also change phase, and during phase changes, we find that the temperature remains relatively constant. So if you've ever worked in a restaurant, you know that a lot of times they like to use ice baths. So as long as there's both ice and water in that bowl or that container, it's at 0 degrees. And once all the ice melts, then the water starts heating up. So as long as you keep ice in that ice bath, it's going to stay at 0 degrees. The same way if it's water and steam, as long as there's water and steam, then it'll stay at 100 degrees. And if you contain the steam and keep heating it, once all the water's gone, then the steam heats up. And the steam gets much hotter than 100 degrees. So, for example, in steam power plants, we use that, right? We use steam that's much hotter than 100 degrees. So, here's some information you should know. So, for water, it melts at 0 degrees and freezes at 0 degrees. And it boils at 100 degrees. The latent heat of fusion is 78.9 kilocalories per kilogram or 333 kilojoules per kilogram. Note that this is usually given in kilojoules, so make sure when you make the conversion it's there. By the way, that means that the heat is equal to the latent heat of fusion if we're turning something into ice or turning ice into water, and latent heat of vaporization if we're turning water into steam or removing heat to turn steam back into water. So here's so for all of these things can be vaporized, right? So for instance, if you ever use the scanning electron microscope, you have to coat the specimen with a conductive material such as gold or silver. So what you'll do is turn the gold into a vapor and let it deposit on your sample. So let's do this experiment. We're going to take ice. Here's a chunk of 20 kilograms ice, and let's say it starts at negative 10 degrees, and we want to turn it into steam at 130 degrees. So the first thing we have to do is heat the ice to 0 degrees. Then we'll keep heating the ice until it melts. So we'll turn the ice into water at 0 degrees. And then we'll heat the water to 100 degrees. And then once we have turned then we'll keep heating it. And once all the water has become steam, we can heat the steam to 130 degrees. So the first thing we do is heat the ice. That's the mass of the ice, the specific heat of ice times the change in temperature. Then we melt the ice. That's the mass of the ice times the latent heat of fusion. Don't forget, this is in kilojoules, right? So you have to multiply it by 1,000. Then we heat the water. We get the mass of the water, the specific heat of water times the change in temperature. And this time the change in temperature is 100 degrees minus 0 degrees. Then we turn the water into steam. It's the mass of steam times the latent heat of vaporization. And then we can heat the steam. That's the mass of the steam, the specific heat of steam, times the change in temperature. So we get 2010 joules kilograms degree C, and our change in temperature is 30 degrees. The graph would look something like this. So we heat the ice. We melt the ice, and during that process, the temperature remains constant. Then we heat the water, and then we turn the water into steam. And as we turn the water into steam, the temperature remains constant. And then we heat the steam. So let's finish off with talking about the types of heat transfer. There's conduction, convection, and radiation. Conduction is heat transfer through thermal contact. So two things are touching, one's hot and one's cold, and the heat runs from hot to cold naturally. Then there's convection. We heat a fluid, and then the fluid moves, makes something else hot. And finally, radiation. This is heat transfer through electromagnetic waves. So if we want to find how heat conducts, we can look through heat transfer through some material. So if you think about it, it's going to depend on how long the material is, the cross-sectional area of the material, and what we're going to do is we're going to take a hot chunk and keep it at a constant temperature, and this cold and keep it at a constant temperature, and then we'll put a sample in between. We're going to look at how much heat flows. So power is equal to the amount of heat divided by the change in temperature, right? And what we find is that it's equal to some constant, which depends on the material, the cross-sectional area, right? So it's easier for heat to move. The longer it is, it's going to slow it down, and then the change in temperature. So if the difference between T1 and T0 is 0, I'm sorry, if the difference between T1 and T2 is 0, they're the same temperature, no heat's going to flow, right? But the bigger the difference, the more heat's going to flow, the heat's going to flow faster. The thermal conductivity you can look up in a table, and it's listed right here. Engineers like to use something called, so here's an example, right? T1 is 35, this is 0.2 meters long, the cross-sectional area is 0.4, and T2 is 5 degrees. And don't forget, a joule per second is a watt. So we get 0.84, 0.4 meters squared over 0.2 meters. The meters cancel out, the degrees Celsius cancel out, and we get joules per second, which is a watt. So once we know the rate of heat transfer, we can figure out how long it takes. So for instance, how much heat is transferred in an hour? We just take the number of joules per second and multiply it by 1 hour, putting it into seconds, and we end up with 1.81 times 10 to the fifth joules. Engineers like to use something called the R value, and the idea is that the thicknesses are going to come in standard sizes. So for instance, if you go by drywall, it's going to either be a quarter or a half or 3/4 of an inch, right? You can't just get any size. So we use the R value instead of that. So the R value is just the thickness divided by the thermal constant. And for the engineers, you could look at this example and see how it works. For convection, we find that what happens is the equations are really difficult. So we're not going to give you an equation for that, right? But what happens, for example, is we have a chunk of air above this steam heater, like you probably see in old buildings. And what happens is this chunk gets hot, it expands, it becomes buoyant, and it rises to the ceiling. And then cold air comes in and fills in, and we get this natural circulation. If you ever notice, these things don't have any fans or anything, and yet it gets the whole room hot. So this is through convection. Another good example is if you watch water boiling, right? What happens is the water at the bottom becomes hot, it expands, it heats, it rises to the top. But the equations are really complex. So I don't know if you can tell what this is. I'll give you a second to think about it. So this is oil heating on the stove, right? And you see all these crazy cracks and things. So the equations are really difficult, but once again, all that's happening is the oil at the bottom is getting hot, expanding, and rising to the top. For radiation, right, we have heat transfer through electromagnetic waves, and I'll just explain this more in class. And what we see is that a good example is the sun, right? We know it's not conduction that's causing this, and we know it's not convection that's causing this, right? There is stuff coming from the sun, but most of the energy is coming from electromagnetic waves. All right, well, thank you, and we'll talk soon.